I know.
We can talk about homework 4 if you want.
Good. I could just do homework 4 again.
Then we can just turn in the same thing that we turned in last time.
I don't know, I'm kind of holding out hope that I'll get more points for this one than for homework 4.
You didn't get much from here.
Oh, I did get points for homework 4, but I lost 2, and that bothers me. I'm one of those students.
Yeah. All right, everybody turned in homework 5. So we can talk about it without fear. All right, so any questions on homework 5? How was question 1?
Challenging,
Challenging? Good stuff when you're done?
I hope.
If I did it right, then it was good stuff.
All right, that's kind of a classic use of induction. Like I keep saying, if you can see how to generalize something, how to take something one step further and you want to generalize it to n steps where n can be any number, that's where you can use mathematical induction. So you assume it's true for n variables and then you try to show it's true for n plus 1 variables. And that plus a base case of 2 variables gets you the whole thing. Does it work for 1 variable?
Yeah, easy way.
Kind of in a vacuous sense. X bar equals X bar.
Is that fine if we start with 2 variables?
Probably want to start with 2 because 1 is not really using De Morgan's. So yeah, I think I suggested 2. Yeah.
I didn't really understand 3.
3. Function maps from the set of integers 1 to n to the set 0, 1. So and to be a function, the only requirement is that each number here maps to one number here. We're not saying it's injective or surjective or anything else. We just need to associate with each number in this domain a number in the range. So to define a function, we have to say what each of these things is equal to. And that completely defines the function. Right, if I tell you what the sign of every number is, then you know what the sign function does, right? If I tell you what the square root of every number is, then you know what the square root function does. So if I tell you what f of every number is, then you understand everything there is to understand about this function f. That make sense?
It's asking how many possible functions there are.
So how many different ways can I give f a value for each point 1 through n?
2 for each.
Right, how many different ways can I give f of 1 a value? 2. It could be either 0 or 1. So there's 2 choices in defining the value of f of 1. I also need to define the value of f at the point 2. And I've got 2 choices, yes. So the product rule, total of 2 to the n ways that I can fill in the right side of these, and once I've done that, that's a unique function.
It's basically question 2 part A, just differently phrased.
Yeah.
I can't believe I didn't spot that.
And since we're going into 0, 1, we can also think of this as something we could write with a truth table. And the number of truth tables you have with n rows is 2 to the n. And you can just think of this as an n-bit binary number. And n-bit binary numbers extend from 0 to 2 to the n minus 1. So there's a total of 2 to the n possible binary numbers with n bits. So all of those lead you to the same 2 to the n.
So this only works because we have a domain of integers between 1 and n and a range of 0 and 1. If it were any real number between 1 and n, output it to any real number between 0 and 1, this wouldn't be a finite definition.
That's correct. If we were going from R to this, infinite number of, and I'd say it's probably, might be bigger than the cardinality of the reals.
There's a function that maps all real numbers to 0 or no, to 1 or -1
Mm-hmm.
based on whether or not they are rational, I think.
Okay.
I don't remember what the name of it is, but the graph of it looks wacky.
That's a sick function. So f.
So rational would go to 1 and irrational would go to -1 or something like that.
Yeah.
Something like that.
And one interesting question is that function continuous anywhere? And I think you'll find it's discontinuous everywhere,
Yeah.
Yeah.
which is a little disturbing. And it smells a little bit like Brownian motion, which is a continuous function, but its path is discontinuous everywhere. So like a pollen particle floating in water traces out a path that's discontinuous everywhere. The path is continuous, but it changes direction continuously. So it's differentiable nowhere. And that gets into like fractals and good stuff like that. So yeah, that's a really cool function. If you were just going from reals into there, so that's one possible function, but I'm thinking, I don't know, what is the cardinality of that set of functions?
This one, the rational and irrational one?
Of this.
2 to the infinity.
I'm thinking it's like 2 to the cardinality of R, which is going to have larger cardinality, because that's the cardinality of the power set of R. And I think we've said, but we definitely haven't proven the cardinality of a power set is always bigger than the cardinality of the set. Double check that, but I'm pretty sure. So Aleph 2 is no bigger than the power set of the reals. So yeah, this is why we do discrete structures, because we don't have to deal with reals. Other questions?
Can we go over number 4 real quick? Did something on that.
Sure. So this is a weird application of pigeonholing. And it's probably in yesterday's video, but maybe we can do it a different way. So you're picking n integers, and you want to know how many of them are going to add up to 11. And the hint was to put these things into buckets, so that if you have 2 numbers in a bucket, they add up to 11. So if I pick 2 numbers like, I don't know, 5 and 8, I could put my 5 in here, and I could put my 8 in here. And since each bucket only has 1 or 0 things in it, I know that none of my numbers add up to 11. But if I pick the number 6, that goes into this bucket. Now I know I have a pair of numbers that add up to 11. Because the way I've set up these buckets, if you put 2 things into a bucket, they're going to add to 11. So how many numbers can I put in here without any of them adding to 11?
5.
I can put in 5. I can put in a 1, a 2, an 8, a 7, and a 5. And I know no pair of those add up to 11. Because none of my buckets have 2 things in them. But no matter how hard I try, no matter what I put into these, if I try to add a 6th number, it's going to have to go into one of these, and that bucket's going to have 2 numbers that add to 11. So if I have a 6th number, I don't know, maybe I'll pick a 10, now I've got one thing that adds up to 11. And if I pick a 7th number, it's going to have to go into one of these buckets. Maybe I'll put in a 4, and that'll add up to 11. And if I pick an 8th number, it's going to go in one of the 3 remaining buckets, and I'll have another pair that adds up to 11. So you can wave your hands and get to the answer of 3, And then you can sort of make it more rigorous using the pigeonhole principle.
How many points would get taken off if there was one number in each? Because there's, like, I considered one side a number.
10,100,000 points.
There's the negative points you promised.
There's the negative points, I promise. I'd probably will grade one of these questions, and it probably won't be 4. Because 4s are pretty subtle, and I'll probably grade some part of question 2, or maybe question 6.
Sounds good to me.
But I look at all the questions, and if you don't have anything for a question, then there might be a point deduction. Because my goal is to make sure you do the homework, and then to grade some part of it.
So with the pigeonhole principle would it be that you had 8 integers and 5 buckets, so 3 of them have to have pairs?
Exactly, yeah.
Alright. When I was doing it, it felt too simple.
It is pretty simple.
Yeah.
It's really just using the word pigeonhole principle somewhere in there. And then your hand waving suddenly becomes like more rigorous.
More profound.
Hand waving intensifies.
And people who don't know the pigeonhole principle will just kind of bow and back away. It's like, oh, you're right, you're right.
I've been seeing that a lot lately when I scare people with this class.
I think those quacks talking about pigeons now.
Yeah. There was a story I read as a kid, I think it was true, about someone who proved that God existed. And they were challenged, and they were like, you know, threatened with death or something if they couldn't do this. And they were a mathematician, and they pulled out a bunch of mathematics, and at the bottom of it basically said, so God exists, and nobody could like argue with it because they didn't understand the mathematics. So it got off. I should look that up again someday.
It's baffling bullshit, I guess.
Well, basically, it's the way of proving unprovable things.
Yeah, yeah. Or say this is left as an exercise. Yeah.
So when we're using induction, I'm just thinking back to the horse problem and how our base case, our n implies n plus 1 didn't apply to the base case. But I've noticed that we don't really ever actually worry about whether n implies n plus 1 applies to the base case that we give. Like
We do, but sometimes we might brush over it.
you don't like explicitly.
But like in this case up here,
Yeah, that's a great example of that, where the first one would not apply to it in DMT. I mean, that's what I'm saying, like, you need to start with 2 variables, because
yeah, so
you're
I
really
said
not
n is
saying-
bigger than or equal to 1, so we're assuming we have at least an A0 and an A1.
Yeah.
And we need to say, you know, De Morgan's theorem assures us that this is true.
Because you know that DMT holds true for 1 by itself, but it's not really De Morgan's theorem, that's just saying that.
That's just saying x bar equals x bar.
Right, yeah,
Right.
it's not really doing the operations.
Yeah.
Well, and even that, I mean, is what you want, but it doesn't, like, then saying P of n implies P of n plus 1 doesn't explicitly say that that implies P of 2, for instance.
But when we do our proof that P of n implies P of n plus 1, if that proof required us to do something with, say, 3 of our elements, then we could say, hey, we haven't proven that P of n is true for any case that has at least 3 elements. And that's what happened with the horses. We broke our set into everything up to the last and everything, excluding the first, and we said there was some overlap there. That requires there be at least 2 things in
Base case.
yeah.
Yeah.
But when you try to show this is true for n plus 1, so let's pull this out because it's a good example. So given that, that's DMT for n. So this thing is equal to this. And DMT does tell us that if we have two things ANDed and we inverse, so we have this thing and this thing, that's equal to, this is for DMT of just two things actually, it's equal to this, OR with this. This is actually just using De Morgan's theorem for n is 2, or for n is 1 actually.
And then you can just say that Pn is the first term is Pn, and then you get the whole.
Yeah, and since we've been given this, right, we assumed that this was equal to this, so we replace that with that, and we OR that, and then you just get rid of the parentheses. And it shows you that this is equal to this. But we needed to use P of n minus 1.
Which is like, if you change the first term from De Morgan's theorem, if you use A0 as in A and A1 as in B, so the first term is actually just A and the second one is just B, which is equivalent to,
Yeah, these.
yeah,
Yeah, so it's just A, B bar.
yeah, which is from the De Morgan's theorem, it's A plus B, A bar plus B bar.
Right. And so here we're actually using the base case in the proof of Pn implies Pn plus 1. It's not usually that explicit. But we should always be making sure that when we do this step, we've got this. And I think we could maybe come up with a all horses are the same color version of De Morgan's theorem.
What do you mean?
That,
Oh, it works for this, and it works for this, and
Yeah.
it works for all of it.
yeah, and maybe I could come up with one of those later. Something where we have something like De Morgan's theorem, but it's not actually true. But if we assume that, we can still show n implies n plus 1. And we get something that's meaningless because the base case wasn't true. Or something where we have this true for 2 variables and it's not actually true for 3 variables, and we show this, but we only show it for when n is at least 3.
Yeah,
And
yeah.
if we can't show it for 3, then we can't show it for 4.
That
But
was
if we
the
show
whole
it for
problem.
2 and then we prove this for 3, we haven't actually proven anything.
Right, and that
That's
was
the
the
worst case. Yeah.
But I mean, the problem with that is it wasn't explicitly, like, we're just like, oh, here's the base case, and then we didn't really, like,
Yeah.
have this. So is that usually not the case then? You usually don't gloss over the base case implies the base plus 1 case?
Not unless I'm trying to show all horses have the same color.
Well, it's up to you. If you're proving, it's up to you to prove that your P of n applies to your base case.
Yeah, yeah.
Like when you're the one proving, you have to make sure that it does.
I think that's kind of the thing that I'm starting to understand about this is you can't really use it on everything. You have to make sure that it's a situation that is appropriate to use induction, because if you're not going to make sure that your base case applies and you're not going to make sure that your P of n applies, then you could theoretically just prove anything and just say
Right.
it's true.
Right.
So you have to do some legwork beforehand to make sure that the things that you're saying actually make sense,
Yeah.
that they follow.
Right, so I mean, here's a reductionist example. Right, prove n equals n plus 1 for all n bigger than or equal to 1. Right, well, P of n is the proposition says n equals n plus 1 if P of n is true, then n plus 1, and do algebra, n plus 1 equals n plus 2 equals n plus 1 plus 1. Therefore, p of n plus 1 is also true. So we've proven p of n implies p of n plus 1. But we can't say, therefore, p of n is true for all n, unless we also have some base case that we know p of n is true for. And we don't.
Yeah, I don't know, I guess I just kind of been seeming like we just assume the base, p of n applies to the base case generally, but I don't know, maybe I'm just...
Well, with De Morgan's, did we?
Well, I mean, I feel like this one actually makes sense. It just kind of reminded me of the fact that I was wondering about that.
Yeah, we may have been getting sloppy and stuff on the board. But the stuff that we've done, you should be able to go back and actually show the base case is true.
Right. And I mean, you can. Okay, yeah, fair enough then.
The subtler part is, are we using something beyond the base case in our, is it actually a relevant base case?
Mm-hmm.
Right, or are we using something, are we assuming something about P of n that doesn't apply to the base case?
Yeah.
Like we can find the largest and smallest element in the set that are different from each other. Well, that only works if we have at least two things in our set. But if we only showed a base case with one element in the set,
They're all the same.
yeah, and then we assume that we could pick a largest and the smallest distinct element and then prove this. We still haven't proven this is true for everything because we don't have a base case that our proof applies to. That's another version of the horses, I think.
Mm-hmm.
Other questions? Anybody thought about induction on like uncountable sets?
I was under the impression that that did not work distinctly, and
It
we
doesn't.
proved that or something.
But I'm
with
wondering if
shared
there's a way
case.
to make something like induction that works.
Well, if it's not countable, you can't assume that you're covering everything.
Yeah.
I mean,
Yeah.
that's the whole point, right? I
Right.
mean, you're proving one case, you're proving that one case implies the next, and then
There is
like,
next.
as part of that, it's proving it for every single possible case because you're starting at the beginning and going
Yeah.
forward. But if you don't have a way to count the next thing, you all you've proven is a base case and that it implies the next, but what you don't even know what the next is.
It could be complete dribble, but what if we did it recursively? Like, suppose we took the real numbers, alright? And I was suggesting this a while ago, but we hadn't done recursion there. And you did it on a decimal basis.
Mhm.
So you would basically sort of iterate over it for 0.1,
Mhm.
0.0, 0.1, 0.1, and for each of those you would iterate 0.01, 0.02, and then for each of those you'd go all the way down recursively
Right.
doing induction.
Yeah, and Jordan and I have been talking about that also. And I think the problem is that will get you to any number with a finite number of digits eventually. But I don't think you'll ever get, say, to exactly pi.
Can we not do infinite recursion?
You can, but to be countable, you want to say after some finite number of steps, I'll get to this
That's
number.
true. It doesn't solve that problem.
But here's a similar idea. What if we pick random numbers? If we pick random real numbers,
Okay.
will we eventually,
So your next one is a random real number, right?
yeah, will we or will we not eventually stumble across pi?
But how do you prove that the random numbers have the properties similar to your proof?
I don't know, I don't even know what a random number is.
Yeah, how do you prove that you're choosing something randomly? And then you have the density of real numbers,
So we
right?
take the time before a nucleus emits an alpha particle.
But doesn't the density of real numbers state that even if you were picking random numbers, you'd never hit every real number? I mean,
But would we hit pi? Either we would or we wouldn't.
that's a hard question to answer.
I think
You're
this
just
is
moving the
above my pay
goalpost,
grade.
you're not actually addressing the issue.
Maybe.
But can you even hit a number if it's a real number? Because it goes on for...
It's possible that this thing emitted an alpha particle exactly pi seconds after I said go.
But just because you hit pi doesn't necessarily mean that you hit everything.
Right.
Could you...
I mean, because if you hit
But
pi,
that's-
did you hit a number between pi and 4?
Right, but I'm just picking one particular number, pi. I could have picked one.
Right. But for any number that you do hit, there's another number that you didn't hit, right?
Maybe.
Because of the density of real numbers, right? You can always subdivide two numbers. And
Well, yeah,
find a new
that's
number.
that's what countability would tell us, but I'm asking intuitively, does that make sense?
Not really.
No, I don't think so.
So I don't know. Ungraded homework question 4.
No.
Speaking of which, did you get anywhere on the Fibonacci?
I didn't.
No.
I was playing with consecutive zeros and subtracting off from powers of 2 while I was swimming. But and I forgot to breathe. No.
That sounds like a great way to drown.
Why am I not surprised?
But I was getting bogged down.
That's what floaties are for.
Yeah. I was getting bogged down differentiating these cases where I had consecutive zeros that were actually shared in a chunk, and subtracting those out was tangling me up.
You just gotta subtract the intersection, man.
Yeah, maybe.
I don't know. Made it sound easy.
Yeah, I mean, subtracting the intersection would take care of this. But when they actually overlap, that seemed to be tripping me up.
You get like more results than you actually want.
I think so, yeah. Because just counting the number of ways that we can put a pair of zeros and a single pair of zeros, right, there's 8 places or 7 places with the overlaps.
I'm still thinking about what we were just talking about.
Okay.
So, pick 2 random numbers.
Mm-hmm.
If you pick a number between those 2 random numbers, right?
Mm-hmm.
You've just proven that you found another number that you haven't hit before. Maybe.
Right.
So, by picking 2 random numbers, you will always be able to find a number in between that you can't say that you've picked before. Because you can always get a new number in between 2
Okay,
numbers.
so you could pick any set of numbers, take the 2 smallest, and pick a number in between them.
Right.
And there's a number you haven't picked.
Exactly. Because you always can find a number in between 2 real
But that's
numbers.
up to a given point n. That would work for the first million numbers. I can show there's numbers I haven't picked, but how do I know that I won't eventually pick that number?
Because when you do pick that number, you can use another number that you picked to show that there's another number in between the 2.
I agree there's another number, but I'm going to pick that tomorrow.
But then you can take the number that you just picked and the number you picked tomorrow, and then pick a number between those.
Yeah, and I'll pick that the next day.
This is vaguely reminiscent of a lot of science arguments.
Yeah.
The creationist debate. There's a new gap in the fossil record. Okay, we found that gap. Okay, now you've created yet another gap.
Yeah.
And by
You're just
saying that
moving the
you
goalposts.
Right.
and if you pick that number tomorrow, you can keep picking the number tomorrow, but what you're saying is that you'll always be chasing the next number. You're never going to.
But the same is true of counting. If you say you can count up to some number n, I can say you haven't gotten to n plus 1 yet.
Mm-hmm.
But the integers are countable.
But
It's not saying you'll get to every integer by a certain point in time. It's saying if you count long enough, eventually you will get to any given integer. And so if you make enough random guesses, 1 per day, will you eventually guess every number? And the answer has to be no mathematically, but intuitively, it's not sitting well with me.
You should be able to get to like pi and stuff like that, so
Yeah.
eventually.
But there is a difference between real numbers and integers, right?
Yeah.
So the idea that you can eventually count to any integer does not necessarily follow for real numbers,
Right.
because of the way that you can always the
Yeah.
density of real numbers, right? You can always find one in between 2 real
Right.
numbers. So you can't necessarily.
But you can always find a rational between any 2 rationals also, but the rationals are countable.
I think a number like pi is going to be like a set of numbers of integers. So we are not talking about all the real numbers, we are talking about very specific set of numbers, which are the digits of pi.
Right.
So something like the programming high level we were talking in
Yeah.
224. We can do that for infinite times, and we should hit that, I think.
Would we ever hit the random number 1?
Yeah. If we have infinite number of choices for any digit, and we have infinite digits, so infinite times for
Why
infinite
would 1
digits.
be easier than pi?
It's not even.
Yeah, if it's
It's
truly
easy.
random.
Yeah.
It's same. I think we can hit that.
Yeah.
Because if 1 is saying 1.000, but the random time is we are hitting 0 randomly.
Right.
Well, you're trying to impose a countable system on a set that we've proven is uncountable.
Yeah.
So, countability theorems should.
Yeah, like I say,
apply.
mathematically, it's got to be true that we're going to miss numbers, most numbers. But intuitively,
What are we
Well,
trying
if
to
you're
hit?
arguing intuition.
Are we trying to
but
hit all the
if you
numbers?
can punch holes in your intuition, then there's hope for extending your intuition. I think.
This is actually why it's
I mean,
frustration.
so if you choose like any random number, so like there's an equal probability to hit any real number, right? If you can somehow prove that for any random number this holds, then that's kind of what you're talking about, like something similar to induction that would
Yeah.
prove things for real,
Right.
like a cardinality of.
Right.
So it doesn't really matter that you hit every one, just that any one that you could hit holds
Gets hit
true.
eventually.
Just holds true for the proposition.
Yeah.
Yeah.
But I don't really know.
That's probably unanswerable.
That's possible.
Right now.
I think he's just messing with us.
I'm messing with myself.
It's fun. Can pi be represented in infinite base?
I've been working on my infinite base notation, and if you can represent rationals in it, like you would represent any other rational, but by definition, the way that this is set up, you cannot represent reals in it.
Because is it something about like the way the symbols are set up that eventually it would just be like impossible to draw?
The symbols are based on the idea of the prime factors for composite numbers and a system of creating new symbols for prime numbers. So I guess you could just do your symbol dot and then you would for any other number system, but you'd basically just be using 1 through 10 or 0 through 9 again. And at that point, you're not using an infinite number system, you're just using a different version of base 10.
Yeah. Infinite base. Yeah, I was thinking about how you would represent like decimals even. It gets weird.
I'd rather not use decimals, I'll just use, because decimals are based on base 10. So in this case, you would just be representing them as a fractional.
Yeah.
You ever work base 1?
And that's just ticks.
That's just ticks.
It starts base 1,
Yeah.
and then it gets more complex.
So I pulled this up yesterday when I was looking through some stuff. We were talking about Fibonacci numbers, so just some interesting observations in here. So the lily has 3 petals, buttercups have 5 petals, chicory has 21 petals, daisies have 34 or 55 petals. Those are all Fibonacci numbers. And this also talks about the number of spirals. For example, in a pineapple, if you start at the top and you count clockwise or counterclockwise and see how many of those little segments you have until you get to the bottom, it's usually 8 in one direction and 13 in the other. And those are consecutive Fibonacci numbers. There's lots of stuff online with examples of this and discussions of how to properly count spirals. And you can have fun in the produce section at Freddy's. Playing with that stuff.
Kick you out.
Yeah.
Take the petals on the artichokes or whatever.
Stop doing that. All right, so I posted homework 6. Pretty straightforward. Question 1, bacteria population of 25 triples every 2 hours. So more interesting version of what we did the other day. So find a recurrence relation for the population, state an initial condition, and then use those, try to find a closed form formula for the population at time t. Question 2 is looking at 2-digit numbers between 10 and 99 inclusive. How many contain no 5s, how many contain 1 5, how many contain 2 5s, how many contain either 1 or 2 5s, and how many contain either 0, 1, or 2 5s. Third, an infinite supply of red, blue, green, yellow, and black socks, and you're pulling your socks out of a drawer in the dark, and then you're going to go to the next room and dress. How many socks do you need to pull out to ensure that you have at least one pair? Right? If you just grab 2 socks randomly, you might get a red and a blue, and then you're in trouble. So how many socks do you have to pull to ensure you've got at least one pair? That's a pigeonhole question.
Yeah.
Question 4, if you're an octopus and you need 8 matching socks, how many socks do you have to pull? All right, so there's just some exercises to play around with. This is due on Tuesday because there's no school next Wednesday. Yay.
Wait, what is it?
Veterans Day,
Veterans Day, yeah.
also known as Get to Sleep Day.
That's Wednesday.
Yeah, well,
So yeah, 11th, Clark's closed. Or there's no classes at least. I don't know if Clark's actually closed.
Campus is closed, it's not.
Yeah. Alrighty. The heck are we up to now?
We were going to talk about Boolean Algebra and
Boolean
Morgan.
stuff, right?
So we're computer scientists, we can never read the full thing.
I know. Alright, so let's talk about probably a review in most cases. So Boolean algebra. So George Boole, 1800s, was studying logic and reasoning and came up with this concept that just happens to work really nicely for computers, and led to things like the difference engine that Charles Babbage designed but could not build, and Ada Lovelace wrote programs for it, but it was all theoretical. But that's a fully fledged programmable computer that was developed in the 1800s, and unfortunately it was too mechanically complex. So if you're into steampunk, right, the idea is, what if people had built a difference engine? It would have been powered by steam because we didn't harness electricity at that time, so our first computers would have been steam powered, and probably all of our automation would have been steam powered, and so we'd live in a world where everything had little valves and boilers and copper tubes on it and stuff, instead of plugging into the wall and using transistors and so on. So there's the whole sort of steampunk mythology from there.
Maybe, like, was it all just a theory, or did he actually, like, make schematics for it?
I think he had designs for it, but the machining wasn't available to actually make all the gears and stuff. And people have made it since then.
I've also heard that he was just too pedantic and a perfectionist to manage it.
I can believe that. So what is a Boolean algebra? Well, we work with a set of 2 things. So those are the only elements in our universe. So 2 elements and 3 operations. So addition, multiplication, and negation. And if we think of B as just a set containing these 2 elements, remember we talked about a Cartesian product. In general, a Cartesian product of 2 sets is just a set of all pairs of elements such that the first element comes from the first set, the second element comes from the second set. If we take a Cartesian product of a set with itself, we just get a tuple of elements contained in that base set B, and we can call this B squared. And so we can think of B to the n as the set of n tuples. So now we've done enough math to make this mathy. And so we can define a function from B to the n to B, and we call that a Boolean function of degree n. And when we write something in 250 like f of a, b, c equals a, b bar, or b, c, we're writing a Boolean function of degree 3 in this case. And it maps from all three tuples of 1s and 0s into the set of 0, 1. So this function f is actually defined from b cubed to b. And when we write a truth table, we're showing each of the elements in this set, and we're showing what it maps to. So we're just defining this mapping by showing the value of f at each point in its domain. So if we think of these functions, we can compose them so if we have two functions f and g, we can define a new function which we write f plus g, and it takes an element x to the following. Just the sum of f of x and g of x. And we can define the product of two functions as just the product of their points. So we can apply these operations on functions themselves as well as points in our space. And x is a Boolean variable, which means it's got a value of either 0 or 1. All right, so let's start tomorrow with identities. We'll go through the various identities that apply to Boolean variables and functions. And then we'll talk about duals, and we'll talk about sum of product and min terms and product of sum and max terms and k-maps and all that stuff that I know you miss from 250. Functional completeness, gates, adders, and that will probably take us through the week. All right, so we'll start with identities tomorrow.
Well, I guess I'll be able to help 50 students better.